Okay, now we are live. Okay, let's introduce the last speaker of the day, Juliana Lopes from Unicam. First, I would like to give express our gratitude to Juliana because she's helping with the Zoom and everything is working well thanks to her. So I thanks Juliana for helping us. And then Juliana is going to talk about the existence of solution for a non-thermal Navier-Stokes Allen system with thermo-induced coefficient.
Okay. Thank you. So first of all, I want to thank the organizing committee for the opportunity to give this talk today. And this is a joint work with Professor Gabriela Pans. So in this work, we studied the existence of solutions for this non-isothermal Navier-Stokes Allen system with thermo-induced coefficients. So this system can be considered as a model describing the motion of a mixture of two viscous incompressible fluids with the viscosity, thermal conductivity, and the interfacial thickness being temperature dependent. So this is a more general system than the previous ones considered in the literature, involve temperature dependence in all main coefficients. So this system consists of the Navier-Stokes equation coupled with the phase field equation given by a convective Allen equation and the energy transport for the temperature. And we investigated this problem in this space where omega is a bonded domain for R2 with a smooth boundary D omega. So we just study this problem in R2, and I will explain later why these restrictions in the dimension. Okay. After that, U represents the mean velocity of the fluid mixture. P, as usual, is the pressure. Phi is the phase field that represents the volume fraction of the two components. Theta is the temperature. Nu is a positive function of theta that represents the viscosity of the mixture. Epsilon is a positive function of theta that is a small parameter related to the interfacial thickness. Kappa is a positive function of theta, which represents the thermal conductivity, and F phi is the potential energy density. So, and we complement this system with the following initial and boundary conditions. So we have the boundary conditions for U and normal conditions for Phi and theta. So the strong nonlinear coupling between those equations due to the temperature dependence brings new mathematical challenge that only allow working in dimension 2. Moreover, the existence of solution will be just local in time, but no restrictions on the size of initial condition is imposed to this system. We observe that for this system, we cannot find an energy inequality for this system, even under restrictions on the initial size of initial conditions. So to obtain lower, so the lower and the higher order estimates cannot be obtained in a separated way for this system. To complement the hypothesis about the system, For the potential energy, we will consider F being a C2 function that satisfies those properties here. We observe that the classical double potentials given by this satisfies those conditions, and these conditions here implies that there exists some positive constants such that F and its derivative satisfies this. Moreover, this property here allows to guarantee the maximum principle for the phase field equation. So by the maximum principle, I'm sorry, F and its derivatives will be bounded. And for the viscosity, interfacial thickness, and the thermal conductivity, for the viscosity, we will suppose that it's a C1 function. For epsilon and the kappa, they will be a C2 function that satisfies that they are positive for all S in R. However, as the maximum principle for the temperature will be true, so we can assume that there exist positive constants, mu 0, epsilon 0, and kappa 0, such that those functions here is lower bounded by those constants. And moreover, as the maximum principle for temperature will be true, those functions and its derivatives will be bounded for all S in R. Right. Just a review about this system. So this system under consideration was previously studied by us in two different situations. So in the first one, we consider the viscosity coefficient being temperature dependent. So in this case, the well-possedness of the model was established, showing the existence of global weak solutions in dimension 2 and 3, and showing the existence and the uniqueness, which will be global in time strong solution in dimension 2, and it will be local in time strong solution in dimension 3. We observe that in this case, no restrictions on the size of the initial data was required. In the second case, we also allowed that the thermal conductivity to be temperature dependent. So in this case, we showed the existence and the uniqueness of local strong solutions in dimension 2 and 3 for any initial data. So when we do not impose any restrictions in the initial data, we guarantee the existence of local strong solution in 2 and 3 dimensions. And when we impose that the initial temperature is suitable small, we could show the existence of global weak solutions and the existence of uniqueness of global strong solutions just in dimension 2. So in this case here, we can show energy inequality for the system just under when the initial temperature is suitable small. So when we do not put these restrictions, we just can guarantee strong solutions. And in this case here, the restrictions in the dimensions is because the regularity of the temperature equation that prevent us to apply the fixed point argument in this in the dimension 3. Because such regularity is not enough to show the continuity of the operator. Okay, so before we discuss about the existence of solution for our system, I will state the existence results For the phase field equation with thermo-induced interfacial thickness, because since we haven't worked with this equation before, so because this is the new difficult for this system. So we are going to apply, the idea is to apply this existence results when we treating the whole system. So we can assume that U and theta will be regular enough. So in particular, as U will become from the Galerkin approximations, so we can assume that U is a smooth with a smooth function with divergence-free vector field that vanishes in the boundary, and that theta has this regularity here. So in this case, supposing that P0 is a H1 L infinite function with its L infinite norm less than or equal to 1, then this problem has a unique solution with P satisfying this regularity here. And the maximum principle. And the idea to show this, the existence of solutions is to employ the Freiduc-Galerkin method and guarantee the necessary a priori estimates for the approximated solution. Now, if we assume more regularity for the initial datum and that being more regular, so in fact, this solution phi will be more regular. So if we suppose that P0 is a weight Turing function that satisfies those compatibility conditions here, so in fact, P will be more regular. And to show this, we just need to derive further a priori estimates for the approximate solution. Okay, so now we can discuss about the theorem about the existence solution for our system. So as as I mentioned before, to guarantee the existence of solution, we need to have made the higher order estimates. And because of this, we need to suppose that U0 is in this space. U0 belong to this space, which and the phi0 and theta0 being H2 functions with those compatibility conditions here. So to guarantee the existence of solution, we need to impose more regularity for the initial conditions. And supposing that this norm is less than or equal to 1 to guarantee the maximum principle for phi. So we showed that there exists a small time that we will denote by this capital T star, such that our problem with the initial and boundary conditions has at least one solution that satisfies this wiki formulation and has this regularity here. So U belongs to L infinite H, L2V, and phi and theta L infinite H1 L infinite, L2 H2. Okay. But just one observation that we have for this existence solution theorem, we have stated the theorem with the minimal regularity required to obtain the existence of solution to the system. But in fact, with some additional and long computations, we can show that the solutions, in fact, they are more regular. Indeed, U, in fact, is a L infinite V function, L2 H2 function, and the phi in theta belongs to L infinite H2, L2 H3. Now, I want to give a brief the idea of the proof. So to show the existence of local solution to our system, we will use the semi-Galerkin method. And we split the proof in 4 steps. So in the first step, we introduce the approximated problem. So given omega e and lambda, omega y and lambda y being the aging functions and the age values of the Stokes operator, the idea is to find the solutions um given by this linear combination. Phi m and theta m solutions of this approximated system. In the second step, we show the existence of a local time solution for this approximated problem. So we show that there exists a small time, capital Tm, that depends on the index m, and solutions um, pm, and third time solutions of the approximated problem. And to prove this, we prove this by using the Schauder fixed point theorem. In the third step, we need to obtain a new differential inequality for some norms of the approximated solution, which allows to conclude the existence of a small time that does not depend on the index n. So to do this, we will construct a new differential inequality and combine it with a small data argument for the shifted approximate solution. So here we will denote by um tilde the difference between um and its initial condition, the same for phi m tilde and for phi theta m tilde. So the idea is to show that there exists a small time, capital T star, that does not depend on the index n, such that the solution is defined on this interval. So to do this, first we need to rewrite the approximated problem in terms of this shifted approximate solution. So for the mean velocity equation, we rewrite this like as this, and we observe that the initial condition for um tilde is 0. Using rewriting the phase field equation, we obtain this new one with initial condition for phi m tilde being 0, and having homogeneous minimum boundary conditions. And the same for the theta m tilde. So to get the differential inequality, as usual, we will choose V as um tilde. For the phase field equation, we will multiply this equation by minus Laplacian of the phi m tilde and integrate the resulting equality in omega, and we will do the same for the temperature equation, multiplying it by minus Laplacian of theta m tilde and integrate it in omega. So sum up the resulting 3 equalities and make the necessary estimates. We obtain this kind of inequality, where this capital A is the sum of those 3 norms, and this capital, the function, the capital B is the sum of those 3 norms. So to conclude the differential inequality, we need to be able to pass this quantity here to this side of the inequality. So to do this, we need to prove that, in fact, there exists a small capital capital T star, such that for all t in this interval, for all time in this interval, the function a will be bounded by this 1 over 2c, where c is the constant that appears here that does not depend on the index n. And moreover, this capital T star is a time that is bounded by this constant. So we observe here that in fact, since a at 0 is equal to 0 because of the initial conditions for those functions, because the initial conditions for un tilde, pn tilde, and the theta n tilde is 0. So in fact, this inequality, this is hold true for small times that could depends on the index n. So the challenge here is to show that this capital T star does not depend on the index n. And to prove this, we will suppose by contradiction that in fact there exists some time denoted by capital T n star in this interval, such that this will be less than this constant in this interval, and at this time the function attend this quantity here. So using this in this previous inequality, we obtain this, and now we can pass this quantity here to this side of the inequality, which implies this last one here. Now we integrate it from 0 to t, where t belongs to this interval, to obtain this. Here we use that this capital T star is greater than this one here. Now we using the definition of the capital T star, using this that the capital T star is less than this, we conclude that for all t in this interval, the function a will be less than this quantity here, which is a contradiction with the definition of the capital T n star. So therefore, with this, we could show that this is holds true for all t in this interval. Now, to finish the proof, in the in the last step, we need to pass to the limit as n goes to infinite. And as usual, we need to obtain some strong convergence due to the compactness lemma to conclude the existence of a solution for our initial system. So here there is the references that I mentioned before, and thank you for your attention.
Thank you, Juliana, for the nice talk. Are there any questions, comments? You can, of course, unmute yourself, write in chat, or write your comments. Well, so there are no questions, so thank